So I guess let's get started. From today, we're going to talk about, just in 2 lectures, the topic reinforcement learning. So reinforcement learning is a pretty important sub-area of machine learning, but it does have a slightly different flavor. We're not going to spend a lot of time. We'll only have, just because this course has covered a lot of topics, we are only going to touch on some very basic concepts of reinforcement learning. This lecture and the 2 lectures after. Next lecture, we're going to have a guest lecture on the kind of the broader impact of machine learning, like robustness, societal impact, so on and so forth. And then we're going to have the last lecture, which is also going to be on reinforcement learning. So this lecture is here just mostly because, I think you need this lecture for solving one homework question in homework 4. This lecture will give you the basic concepts so that you can solve that homework question. So, okay, so reinforcement learning. So I think reinforcement learning is kind of like, at least on the surface, it's very different. It sounds like very different from some of the other machine learning problems because there are a bunch of like different things. So maybe just to give you a rough sense on what kind of questions we are trying to solve today. So maybe the running example you can have is that you have you are trying to let a robot learn how to navigate a certain part of like some space, right? So you want to control the robot to do something. So we are trying to solve this kind of like controlling tasks. So maybe you want the robot to kind of pick up some object, or maybe you want the robot to go to some place, so on and so forth. So there are a bunch of differences between RL and supervised learning or unsupervised learning. So the differences, So here are some differences. I'm not trying to be very comprehensive, and also there are intersections, right? So there are certain sub-areas of RL which is more similar to supervised learning. So here I'm just only going to talk about some high-level differences. So the first of all, RL is about sequential decision making. So sequential. So I guess there are 2 things that you need to pay attention here. So the first thing is that this is about decision making. So before, when you talk about supervised learning, you are talking about prediction, right? You are predicting the house price. You are predicting whether somebody has cancer or not. You are predicting some wise, some target, right? So but here, you are not really just only about prediction of what will happen in this world. This is also about whether what kind of decisions you make. Sometimes these decisions are made after you make the prediction, right? Maybe before or after you know that this person might have cancer, then maybe you need to kind of give this person some treatment, right? So that's the different part, right? You have to make decisions based on the prediction. Sometimes you don't predict, you just make decisions directly. That's also possible, but at the end of the day, you are making decisions. And second, this is sequential decision making. So your decisions have a long-term impact, right? So especially maybe think about controlling a robot, right? So if you let the robot go forward at this step, then at next step, like the robot, the configuration or kind of the robot will move, right? So this the decision at this step does affect your decision at the next step. Think about, for example, treating a patient, right? So if you give the patient some kind of pill today, then maybe the patient becomes better, and the next day then you have to change your strategy, or at least the decision you made yesterday probably would affect the decision you make today, and then which would also affect the decision you make tomorrow. So I think that's the 2 important thing about RL, and you'll see that this is kind of like why this is challenging, because you have to consider the long-term kind of consequences. Or long-term kind of like consequences of a decision. It's not like you can just say, I just greedily choose a decision based on the current situation, choose a decision that can make the next day the best, right? So maybe you can make a decision that makes the next day, very good, but then the day after tomorrow, you got into some weird situation, right? So this is, you think about, your life decision. Sometimes you shoot for short-term reward, you do something, but then you missed out, for example, long-term investments in some other opportunities, right? So greedy approach sometimes, doesn't work very well, and in many cases, just purely greedy approach doesn't work. And there are some other kind of like kind of things about, another thing about decision making is the following. So when you make decisions, right, so decisions can give you multiple benefits, right? So one thing is that you are required to make a decision because that's the problem formulation, right? When you control the robot, you have to make a decision. How do you control it, right? You want to turn left or turn right. But another thing about decision is that when you decide what you do today, you also collect information from the environment about what the environment will look like. So decisions also affect you in terms of the information, right? So you can make decisions to kind of query. In some sense, the decisions part of the job is to query the environment so you collect more information. Maybe let's take the treating patient example as another example, right? So maybe your decision could be that I'm going to measure the patient in terms of certain kind of measurement, right? That's another decision. And that decision doesn't really treat the patient, but it does collect information for you so that you can treat the patients, later better. So decisions also give you additional information. So sometimes you have to think about, whether a decision you have to trade off the different kind of like effects of decisions, right? Sometimes the decisions just directly give you some reward, but sometimes the decisions give you reward, doesn't give you reward, but give you information so that you can use that information to get reward in the future. So I use the word reward, which I haven't really defined. So that's another actual difference between this and supervised learning. So here there's no supervision. So no or little supervision. So what does it mean? So for example, if you think about controlling a robot, right? So one supervision could be that some human is telling you that how should you control the robot, right? Some expert knows that how you can play with this robot, but the kind of questions we are solving here are those questions where you sometimes just don't even know what's the right way to control the robot, right? For example, suppose you want to fly a helicopter, right? So if you really fly a real helicopter, there's some training, right? So you have to be trained to be somebody who can fly the helicopter. But suppose you are developing a new helicopter that can fly automatically, then you are trying to figure out what's the decisions you have to make, right? So or maybe think about treating the patient. You have to find out the sequence of treatment you should give the patients, right? It's not like somebody already knows it. If somebody already knows it, then probably the problem is already easy, right? You should just use that expert, policy. But sometimes you are trying to figure out the best way to make decisions. So that's why there's no or very little supervision. So in some sense, you are not really trying to predict what's the best prediction. You are trying to figure out the best prediction by kind of interacting with the environment by some trials and errors. Just because humans sometimes don't know the optimal decisions either. But if you don't have any supervision, how do you figure out what's the best decision? So the kind of the way to deal with is that you have you learn not by imitating some human kind of supervisions, but you are trying to learn from some reward function. So what does it mean is that so humans specify the reward function. So the humans specify what you want the robot to do, right? So if the robot picks up this object, that means success, then that's a reward function. That means reward is high. And if the robots fail to do that, the reward is low. So you specify the reward function, and then you let the machine learning algorithm to figure out how to maximize the reward function. So that's another kind of aspect here. These are not completely kind of mutually exclusive. So I've kind of mentioned this, right? So another kind of interesting feature is that you collect more data interactively. I think this is pretty much what I've mentioned before. The decisions also give you more data, right? You can make a decision to query kind of some information, or even you don't make decisions deliberately to query information, they still give you additional information once you make the decision. So because it's sequential, right? So you make some decision and then you get some data, and this data could help you in the next round to make better decision. Of course, there are many different variants of the reinforcement setting, right? Sometimes, you can assume you have more supervision from some experts, can give you a demonstration, and sometimes you don't have reward function, sometimes, you cannot have interactive collection of the data. There are a lot of different variants, right? So basically, you can add the adjective before reinforcement learning to have a variant. So you can say offline reinforcement learning. That means you have more supervision, but don't have data interaction. You can have other kind of like combinations. But this is the main kind of set of features of reinforcement learning. Any questions so far? I know this is very abstract, but yeah.
Could you go over the little supervision point again?
Yeah. So basically, you don't. So what could be a supervision here? Because you are trying to make prediction, make decisions, right? One possible supervision would be that you let the expert, an expert who knows how to solve the task, to demonstrate how to solve the task, right? So for example, suppose you want to control the robot, and you say, okay, maybe you knows how to control this robot, and then you just demonstrate to me how do you make the robot to solve the task. And that would be a supervision, right? But in many cases, you don't need to have this supervision. Sometimes you don't have the supervision because the humans don't know what are the best way to control the robot. And sometimes you have the supervision, but you don't need them. Or sometimes you have the supervision, but it's kind of hard to collect supervision because you have to find an expert. So that's the basic idea. Actually, but just to be fair, recently, I think in the last 2 or 3 years, people are moving towards more and more like human supervision, because it turns out that there's trade-off, right? If you don't use supervision, you don't use human supervision, that sounds great because you don't need human to demonstrate for you, but you need to collect more data and do have more trials and errors. You have to try out different kind of like ways to control your robot and see which one succeeds and which one fails, and then learn from that. But suppose the humans tell you something, then you don't have to try that many times. You can let the robot fall down less often, right? Maybe without even trying on the robot, you already know how to control the robot just because you learn from the humans. So I think in the last few years, I think people are moving towards using more and more human supervisions. And sometimes you are using like imperfect human supervisions, right? You use kind of like, sometimes they don't have the expert supervision. Sometimes it could be just some data from the past, right? So you have seen the robot going around doing some tasks imperfectly in the past, and you use those data as supervision to learn something better than the past data. That's even possible. But we are not going to go into all of these details, right? So for this lecture, there's no supervision. Just you know nothing about what's the right decision, but you're going to figure out the decision by trying different strategies. So basically, all the algorithms will look like this, somewhat kind of like trials and errors, right? So you start with a robot, you don't know how to control it, right? You don't know how to use it to solve any tasks, and then you try different kind of like decisions, actions, and then some actions, just happens to pick up the object, for example, and some other actions just happens to fail, and then you try to use those actions that succeed. You know whether it succeed or fail because that's your reward function, right? If you succeed, you have better reward, and if you fail, you have lower reward. So you know whether it succeeds, and then you try to kind of like boost the chance to, your algorithm tries to kind of like amplify or boost the chance to take those actions that can succeed in the past. And you kind of do this bootstrap thing, and eventually you find one set of actions or one set of policies that just always succeed with very high probability, and that's how the algorithm, roughly speaking, how they works. So okay, so basically everything is through this reward function, right? So the reward function is kind of the signal you rely on to learn what is good and what is bad. Any other questions?
I think that we collect data interaction. So like, what type of data we are collecting? Is that the performance regarding the reward function?
So the reward is something you collect, but you can also see something more. You can see, for example, when you manipulate the robotic arm, you can see how where the arm moves towards, right? So you can also observe other things I'll formalize that as well. But roughly speaking, you can observe, basically like, for example, if you treat a patient, you can observe something about how the patient, behaves or performs. And if you train a robot, then you can see how the robot kind of moves. Right? Those are additional information you can collect. And sometimes this information is via kind of like a pixel, kind of like you can collect the information via different ways. Sometimes it's from the camera, sometimes it's from the internal like a recording of the system, sometimes it's from something else. Yeah, you can have multiple reward functions in many cases, but then you have to decide which one is more important, how do you balance them, right? So in our lecture, we are going to just have one reward function. And sometimes you can also have constraints. For example, you can say you have one reward and a bunch of constraints which you have to satisfy. That's also a valid setup. Okay, I think I probably have said a lot about the high-level idea, which is probably a little bit hard to map to the real thing. So let me try to define mathematically how does this work. And I'm going to use this running example, a very, very trivial running example. So this running example is that you are trying to control a robot navigating a 1D tape. So suppose you have a tape which is like this. And you have a robot which it sits somewhere. And it can move to the left or to the right. You can take some action, right, to move it left or right. And maybe there's a goal somewhere else. Maybe this is the goal. So you want to move this robot to the goal, which is kind of trivial. If your human knows this task, the person would be able to move it. You just keep moving to the goal, right? That's easy. So, but we are going to let the algorithm to figure out what's the right the strategy. So, so this is my running example, and I'm going to formulate, the set of problems. So the formulation is often called Markov decision process. So let me define a bunch of kind of terminologies. So there is something called state, S, and you can have a set of states. And that's denoted by capital S. So for this example, a state basically is the situation that the robot is in, right? So a state basically is, suppose you have like say 1, 2, 3, 4, 5, 7, 6. Actually, maybe let me just change the goal to be here to be consistent with my note. Maybe I say 10. So a state basically is describing what's the current situation of the robot, right? So here the state is probably 3 because the robot is here, right? And here you only need 10 numbers, there are only 10 states. So that's the only thing you care about, right? But if you really have a real robot, maybe you have to describe this robot in many other parameters or many other kind of like numerical kind of numbers, right? For example, you may describe the robot speed, the velocity, the height, the center of mass, so on and so forth, right? Then you can have a high-dimensional state, right? So like you have a lot of numbers to describe the state of the robot, and the family of the states basically the state in that case will be a high-dimensional vector, and the family of states will be just all the high-dimensional vectors that can describe the robot. Maybe another example would be that if you think about playing Go, then the state would be the current board, right? So where all the kind of like how does the board look like? And then you have a lot of states because there's like 361 entries on the board, and every entry you can have a white and black, and nothing. You have 3 choices, then you have 3 to the power of 361 possible states. So this is the concept of state. And there's a concept called action. Sometimes, typically we use A for action, and there's a set of action. This is the set of actions you can take, which is called A. So in this case, basically these are all possible kind of decisions you can make, right? So and it's called action technically in this language. So for example, here, maybe like I will just allow you take two actions, left and right. You can just move left or move right. And when you control a real robot, probably you can take other actions. You can change you can accelerate or deaccelerate, or maybe you can change the force, at different joints, many other things, right? And if you play Go, then the action is to really just put something on the board, right? Okay, so this is a set of actions, and then I need something called dynamics or transitions to describe how does the actions influence the state. So this is called dynamics, and I think also sometimes it's called transition or transition probabilities. Or sometimes it's called state transition probabilities. So basically, this is the. So basically, you're asking about a question. So I guess maybe let's define a notation. So this is P as A. This is you're asking a question when applying action A at state as, the probability distribution. You're asking where I should arrive at next time. So the probability distribution, probability distribution of the next state. And the next state, often just notation-wise, it's often called S prime. So basically, you're asking. So in other words, P as a Z is the probability of S prime is equals to Z given S and A. So P as A is the probability distribution, and this probability distribution is the conditional probability distribution. Conditional, currently you're at state S, and you play action A, and you ask yourself, what's the distribution of the possible next state? And there's some randomness here, right? So, for robots, sometimes you can think of it as deterministic because you do something and deterministically it moves to some other place. But for many other kind of environments, you take some action, but how does the environment, how does the state changes, is probabilistic. There's some randomness involved. So the randomness is trying to capture on that. So that's why in this sense, so for every S and A, this P as A is a distribution. So P as A, if you write P as A as this, the probability of every state, right? So suppose you have a state S, which is equals to 1, 2, something like this, right? So then if you can also view this as a vector. You say this is P as A 1. This is the chance to arrive at the state 1, and this is the P as A at the last state. Maybe I'll just I think, yeah. S. Maybe I'll just maybe let's just I think I realized that maybe let's take this. Say M is the number of states. So my state is just to have like a M states, 1, 2, 3, 4 up to M. Then you can list the probability to arrive at each of the states and write it as a vector. This is a vector that is in Rm, and this is the probability vector. So this vector itself, all the entries are sum up to 1. Of course, you can also have deterministic transition dynamics, right? So you can say that only one of these numbers is 1 and all the others are 0, and that's a deterministic transition dynamics. That just means that you always transit to the same state given the same action and state, and the same state and action. You always transit to the same next state. Okay, so I think I'm going to have an example based on this robot thing, just to give you a concrete idea. So suppose you say you have this action set, which is L and R, and this means that you push the robot to the left or to the right. But let's say suppose there's some randomness in this environment. Even you try to push it, it doesn't necessarily always move. So with only a good chance it moves. With some chance you just fail to make it move, right? So so maybe let's say suppose so L action say succeeds with probability let's say 0.9, then that means that if you look at if you use this notation, it means that suppose you're at P, suppose you are at P say you're at state 7, and you apply the action L, right? So P as A, S is the state and L is the action. So then you ask what's the chance to arrive at some other state, right? You're at 7, and you try to move it left, but you know that it only succeeds with probability 0.9. That means that with 0.9 you're going to arrive at 6. So this will be 0.9. And with 0.1 chance you're going to arrive at 7. You stay at 7, so that's 0.1. And with 0 chance you're going to arrive at any other places. For example, you're going to arrive at 5 with 0 chance, and you're going to arrive other places with 0 chance. So that's one example of the transition dynamics. And then you can write down the transition dynamics for other state action, maybe just for example, suppose you say P7R. So now you're asking at state 7, if I try to move it to the right, where it should arrive at. We know that it should arrive at 8 with some chance, with chance point. I guess in my example I make it a little bit complicated just to. So let's say R action succeed. I'm just making this up just to make it interesting with probability 0.8. Then it's saying that with probability 0.8 you're going to arrive at 8, the entry 8, so you get 0.8, and with probability 0.2 you are going to stay at 7, and with probability 0 you're going to arrive at any other states. So that's mean P7 R maybe 5 will be 0, and all the other P7 R Z will be 0 if Z is not equals to 7 and 8. And you can define whatever transitions you want so you can write using the same ways you can write out all the transition probabilities for every state action pair. Okay, so that's my kind of description of the environment. By the way, by environment people generally refers to this kind of entire system, right? So how does the how does things change based on your action, right? The environment basically just means this entire system. Okay, so now I have defined the transition probability, and now I have to talk about sequential decisions, right? So far I only talk about one action, right? How does one action affect the system? So when you have sequential decisions, then what happens is that you are interacting with the environment or the system, so like the following. So first of all, you say, I'm going to have an initial state as 0, which is the initial state. And let's say the initial state is given. But sometimes you can also say the initial state is randomly drawn from some distribution. Okay, and then, so what you do is that the algorithm chooses some action, A0, from the action set. So, and then after the algorithm chooses the action, the decision or action, the environment step is that you basically sample S1 from this distribution, right? So you basically translate your state based on this rule that we have described. So you say S1 is going to be sampled from PS0, A0, right? PS0, A0 is basically, if you apply A0 on S0, what's the chance, what's the probability to arrive at new states? And you sample one state, one concrete state from this probability distribution. And then the algorithm chooses A1 and in this action A. But here A1 can depend on what? So A1 can depend on S1 and S0. So S1 is considered as something that is given to the algorithm, right? So you observe S1. After you play the action, you observe more information, and the more information is S1. And then you can play your new A1 based on S1 and S0. And then you just keep doing this, right? So the next round, you just say, I'm going to continue. I'm going to say the S2 is generated from PS1 A1, and then algorithm picks A2. And A2 can depend on all the history, right? All the historical observations you have seen. So, so that's the idea. Okay, so for example, if you really think about this, this thing, maybe you start from 3 and you apply, you start from the state 3, and then you can apply R action. And then with some chance, you're going to arrive at 4. And then suppose you arrive at 4, then you can say, I'm going to decide again what my action should be. And you say, okay, my action should still be R, and then I can observe whether it does move, right? So with some chance, it will move, and you just keep doing this. So, okay, so that's kind of describing the decision process. And there's one thing we haven't described, which is the reward, right? So how do we decide when you succeed or not, eventually, right? So, so the reward function, there is something called reward function. So the reward function is a function that maps, maps the state, the family of states, the set of states, to real number. So basically, sometimes you write it as RS, right? S is a state, and you apply the reward function, you get RS. In some other cases, you can also have a reward function that depends on the action. Sometimes it can depend on the next state, but let's, for the purpose of this course, let's say the reward function only depends on state. So, so basically, for example, for this, robot case, maybe you can say, suppose you want to somehow have a reward function that characterizes whether you achieve the goal, state 6. Maybe you can just define your reward function to be R6 to be 1.0. So achieving 6, give you a high reward, and then you say if R of S is, say, I'm making this up, it doesn't really matter exactly, but you say your reward is very small or even negative if your state is not 6. So suppose you define a reward like this. In some sense, you are encouraging the algorithm to reach the algorithm to reach 6 and not reach any other state. Because for other states, you get negative reward, and for the 6, you get positive reward. Okay, so, but this is only a reward for one step.
Can you have reward for states and actions? So like let's say if you go towards if you take a certain action, then it's more expensive. Whereas if you take a certain other action, then it's less expensive.
Yeah, you can do that. So basically, that's what I said. So your reward function can be a function of S and A as well. In many other cases, but for simplicity, let's just say the reward is a state. The math doesn't change much. It's almost the same. Yeah, and sometimes actually it depends on the state and action and the next state. So you can depend on S prime. Yeah. Okay, cool. But this is only about one step. Eventually, you have to care about the sequential decision making. It's just not about one step, right? So the total payoff is defined to be sometimes it's called total return. So this is defined to be rs0 plus rs1, so on and so forth, plus rst. So this is the total reward. Basically, just the sum up all the reward at all the steps. And now here I didn't specify how many steps we're going to have, right? So if you have infinite number of steps, then this doesn't seem to make a lot of sense because your reward will be sometimes going to infinity, right? If you have infinite number of steps and each step you get a reward something like 1, then your reward eventually will be infinity. And it becomes not very informative because you cannot compare one infinity with another infinity. So, and there are two ways to deal with this. So one way to deal with it is that you say you have a discounted reward. But you have infinite horizon. By the way, horizon means how many steps you're going to play in this sequential game. So, so basically, the discounted reward is the following. So you have rs0 plus some gamma, rs1, plus some gamma square, rs2, so on and so forth. And where this gamma is less than 1 and larger than 0 is the so-called discount factor. Discount factor. And here you have infinite horizon. Basically, it just means that you take sum to infinity.
One thing I can do that tau is a horizon variable, right? Like, is it st?
This is t, but here I still have, I don't know. Like here I'm not kind of being vague, so I'm taking the.
Like in this case, there's infinite horizon, right?
Right. So this is just a demonstration. This is not the total payoff doesn't really make a lot of sense if you if you just do this. But you have infinite horizon, it doesn't really make a lot of sense. It's because it's going to be infinity. So this is the real definition. We have infinite horizon, so you have discounted reward. And the reason why you want to have this discounted reward is that, so I guess there are several ways to think about this. So one thing is that you can think of this as kind of an interest, it's kind of like in the finance where like the return you get, the reward you get in the future doesn't worth as much as the reward you get in right now because there's an interest rate or inflation rate, something like that. So basically you say that you discount what you get in the future by a little bit, exponentially, right? If you get some reward after t times, you're going to have, so basically here the t's term would be like this. So you discount your reward in the future by some factor gamma to the power t, just like like in finance or in economics, your return in the future doesn't worth as much. So that's one way to think about this. And another technical way to think about this is that if you do this, then you even you have infinite horizon, then your total reward is always bounded. So suppose you have, wait, did I? Oh, that's from last week. So basically, suppose your gamma is less than 1 and bigger than 0. Oh. And suppose each step, your reward is bounded by minus m and m. So suppose you have this two. Then you know that your discounted reward, discounted payoff, this is, at most, say 1 plus gamma, the first time you can only get m, and the second time you get m times gamma, and the third time you get m times gamma squared, so on and so forth, right? And this series, will converge, so the total sum will be something like m over 1 minus gamma. So basically, you guarantee that at least you have a bounded return, and this is the maximum return you can get in the best case. So technically, this makes it possible for you to reason about infinite horizon because your return is always kind of at least bounded. There's always a number, a kind of meaningful number for the return. You have some questions? I saw some. Oh, no questions. Okay. Okay. So Right. So if you look at the RL paper in the literature, sometimes also people talk about finite horizon, which means that you just have a hard cutoff for how long you're going to play this, right? So there's another way to formalize the problem, which we are not going to talk about in this lecture, but I'm just going to tell you the existence of such definition. So if you have finite horizon, you just say you have a horizon which is called t. This is basically saying that you just have to stop at t step. You just have to stop at t step. And then your reward will just be, you don't have to have discount factors. You just say, I'm going to add up the first t steps. So this finite horizon thing and infinite horizon, they don't have fundamental differences from a technical point of view. If you know how to solve one, you basically know how to solve the other. Of course, there are some kind of dependencies. If you really care about the theory, so here your all your kind of like dependencies depends on gamma, and here your dependencies will be on t. But fundamentally, they don't really matter that much. But the infinite horizon case is a little bit easier to understand. In terms of at least for the beginning, if you just derive the math is cleaner. So that's why we do the infinite horizon case. And by the way, the gamma, typically empirically people do use gamma, do use the discount factor. And gamma is something like probably 0.99. And sometimes in extreme case, people even do 0.999. So if you're in this regime, in some sense, the way you think about it is the following. So let's say gamma is 0.99. What does this really mean? It means that you have to really take a power that is kind of on order of 100 to make this gamma to the power t to be somewhat different from 1. Right? So basically, 0.99 to the power 10, this is still pretty close to 1. This is probably like, I think this is how to do the math here, right? If you really care about it. So it's kind of like 1 minus epsilon, right? To the power t, this is close to 1 minus epsilon t, something like this, at least for when t is small. So if you really do it, so if you do the calculation, so this to the power to the 10, this is still close to 1. This is probably like 0.9. But only if you reach the power to higher, so you reach the power to 100, then you're going to have this. I think this is 1 over e, something like that. It's like 0.2 about, yeah, exactly. So basically this is saying that the power has to be large enough so that this discount factor starts to matter, right? When the power is only 10, it doesn't really matter. And what exactly this power has to be, I think if you do some careful math, I think what happens is that, sorry, I'm just reusing this part. So 1 minus, so gamma to the power of 1 over 1 minus gamma, this is something like 1 over e, roughly speaking. So only your power becomes 1 minus 1 over gamma, then you start to see the effect of the discount factor. And after that, it decays pretty fast. So in some sense, if you really want to kind of have a way to transit between finite horizons and infinite horizons, then basically this 1 minus 1 over gamma is kind of like your effective horizon length in some sense. Because when t is much bigger than this 1 minus 1 over gamma, then the discount factor just starts to be super small, so then you don't even have to care about those kind of steps. Okay, so I guess finally, after using 6 bars, I defined this MDP. So this whole thing is called MADP. So this whole formulation is called the MDP, Markov decision process. And you can see that this Markov decision process are defined by a bunch of kind of like concepts. So one thing is the set of states. Another thing is the set of action. And the set of transition probabilities, PSA, S in S, A in A, right? So, and you have a discount factor, and you have a reward function. So basically, after you specify these 5 things, then you specify MDP, and that's a well-formulated problem. And the goal of the MDP is that, maybe I'll just write a goal here, even though it's pretty. So the goal here is to maximize so basically you want to find out a way to maximize the a discounted payoff, let's say. So basically, given MDP, you want to figure out how to maximize this discounted payoff.
Just to clarify, like, what payoff and reward range basically the same.
The payoff, I think, means the sum of the reward, discounted sum of the reward. And reward basically means one step. I think people sometimes also call the sum, the summation version, sometimes you call it return. And occasionally also people just call it reward. But I think I like to kind of have a differentiation of the terms just to make it not too confusing. Okay, any questions about the formulation? So far we didn't really do any derivations, right? So just to clarify, so all of these are definitions. Like how do this? It's kind of like a world view. How do you view this world in some sense? Like what's the important concepts and what are the goals? I'm running a little bit slow, but it's fine. Okay, so now the next question is how do we solve this problem, right? So how do we find out the best action? And for starters, we're going to assume that these PSA are given. So you know the transition probability. You are just trying to find out what's the best action you should take to maximize the reward. But in reality, you don't necessarily know the PSA. You don't know the transition probability. You have to somehow learn them from observations. So I think for this course, we don't really talk too much about how to learn the PSAs. So in some sense, you can mostly assume that the PSA, they are given. And the only question is to figure out what's the best action to take. So the first thing to realize is that, there's the so-called Markov property. So I didn't emphasize that, but let me do that right now. So the Markov property means that when you take the environment, advance the state, right, change the state, it only looks at the previous action and the previous state, right? So the environment, how does the environment change the state only depends on the previous state and the previous action, right? That's kind of described in this PSA, this framework, right? The PSA, the next state only depends on the previous state and previous action. So in some sense, your state, there's a Markov property, right? So you only have to look at the previous state to decide what's the next state. You don't have to look at the entire history. So because of this Markov property, it means that you only have to when you make the decisions, you only have to look at the immediate state, the current state. So the optimal decision at time t, the optimal, maybe let's call it action, just to be consistent with the terminology. The optimal action at time t only depends on the state st. Because anyway, like whatever you do, it's like basically after you see st, you can forget about the history because the history doesn't really matter, conditional st, right? The history is independent with the future, conditional st. After you see st, you know everything about the current configuration. So you don't have to use the st to predict, to make decisions and to maximize your reward. So basically, because of this, there's this concept called policy. So policy is a function that takes in a state and outputs action. So I guess technically I'm going to say this is mapping state to action, right? So its action is equals to, it's kind of like action is equals to the policy applied on a state. So basically you only have to look for policies instead of looking for entire trajectory of actions. Because anyway, the way you make decision is that you look at the immediate current state and then you apply some function on the state to get your action, right? So basically, the unknown thing becomes a policy instead of a sequence of states. Does it make some sense?
Isn't this like at the beginning you said we are trying to avoid a greedy algorithm, right?
Right.
Isn't this really greedy that you're just looking at the current state and like set of actions available to you right now?
That's a great question. So the question was that whether you do this sounds like it's greedy, right? So it's not in the following sense. So when you decide what policy you use, you do have to think about the long-term ramification of your action. But it's only that, but the action doesn't depend on I think this is more about you don't have to care about the history. So you don't have to care about the previous history, you just care about what currently, condition on today, right? So what happens today is all that matters, right? I can forget about what happens, I don't care about how do I arrive at this situation, right? So in some sense, like, how do I say it? Like for example, if you have a robot, right? So if the robot already kind of dropped the bottle, you don't care about how the robot dropped the bottle. You just care about the bottle now is on the ground. I have to go pick it up, right? So this is more about forgetting the history. And when you decide the policy, you do have to think about the future. You see that when we optimize the policy, when we find the best policy, we do think about the future a lot. Yeah, I'll get back to that as well. Yeah, cool. Okay, so this is the first thing. So you only have to find a policy, but this policy is not something trivial to find, right? Because this policy is a function, right? So you have to figure out what's the best action for every state. So basically, for every state, you have to figure out the best action, and that will give you the so-called policy. Okay, so maybe one way to think about it is that here, suppose you want to move your robot to the goal, then the policy problem would be that if the state is on the left of the goal, your policy should be taking the right action. And if the state is here, you should take the left action. Right. So and by the way, the policy can also be randomized. Here I'm looking at a deterministic action, right? So you say you have a state, you output a single action. For every state, you have a single action. That's called the optimal policy. But in many cases, the policy could be a randomized function, or could be something like conditional state S. You can output a distribution of actions, and you choose randomly from them. For the purpose of this course, I think we are not going to have, at least for this lecture, I'm not going to have random policy. For the next lecture, I think I'm going to talk about randomized policy. Okay, so now I'm going to, so how do I find a policy, right? So this sounds a little bit easier than finding a sequence of actions, but how do I do that? So let me introduce another notion, which is called the value function. So let's say you have, this is a value function v pi. This is a value function of a policy. This is a function that maps the state to a real number r. In some sense, this is trying to capture the value of the state. So under this policy pi. So basically, this is equals to, so v pi s is defined to be inverse the total payoff obtained of, say, executing policy pi starting from state S. So basically, you think you start from state S and you keep executing your policy pi just every time iteratively. Every time you see a new state, you apply your policy pi. And then you collect some total payoff, total discounted payoff. I always have discounts, just for the rest of the lecture. So I compute the total payoff, and I call that the value of this state S. Right? This is demonstrating how good this state S is under this policy pi. Because if the state S is good, then you have it's a property of the both pi and s, right? So if the policy is good, you get better payoff. If the s is good, if the s is probably at the goal, then you probably get better payoff because you don't have to move anything, right? So this is just, go ahead.
A question about this whole concept of policy that's talking about here in the value function. So when you say that you start the policy from S, is it a policy restricted to a certain state, or what you're saying is that that policy, like you take an action and then it goes to a state S prime, there are 3-4 candidates, and then you evaluate the value function for each of them? What's this like?
Okay, so what's, okay, so.
Like, do you expand to like future states also in this calculation?
Yeah. So maybe let me, yeah, I think that's a good question. Maybe let me just define it. Yeah, this is just the intuition so far. So what does this really mean is that you start with S, S0 is equals to S. And then you say A0 is equals to pi of S, S0. And then you say S1 is equals to, is sampled from P S0, A0, right? So you start with S, and then you take action A accounts the policy pi. And then you say the environment take a step, and the environment draw the next state given S0 and A0. And then you play A1 according to the observation S1, pi of S1, so on and so forth. You play this game, and then you say you look at the reward that you accumulate throughout this process. And until infinity, and you say you take this expectation, the condition S0 is equals to S, and this is definition of the value function. So value function is this is the expected total payoff, expected discounted total payoff of this game, right? The game is, the process is that you start with S, and then you play this policy, and the environment does what it should do, and you always play this policy. So that's the value of this state S.
I have a question on how do you select in S1 and S3, basically all future states, like you're sure of the current state, right?
All the future states are selected by the environment based on S0. So S1 is selected by S0 and A0. And S2 is selected by, if you have, maybe let's just continue here.
I mean, just to clarify, are you going through all the future states that are possible after A0? Or are you just going through because it's possible?
I'm sampling S1 from.
Or you're sampling S1?
I'm sampling from the environment, right? So if the environment is deterministic, I'm just going to talk, it's just fixed. The environment decides it, right? If the environment is random, then you sample one from it. But eventually you take average over all the possible. So basically you simulate your world, with all the possible possibilities, but of course each possibility has different, like each possible future has different probabilities, some more likely to show up, some less likely to show up, and then you look at the rewards for every possible reward of the future, and then you take average over all the possible rewards.
So you take the average of all possible rewards for S1, right?
For all of them, right? S0, RS1, RS2 until R. So basically, you apply this policy and you try this policy in the real world, and you can, in the real world is stochastic, something random may happen, and but you just try this out, and you collect all the reward and you take expectation of the reward, the total reward. This is a definition. I'm trying to give you how do you really do it? That's a different question. This is the definition of the concept. Okay, so why I'm defining this? I'm defining this because there are two reasons to define this. Well, one reason that this is kind of capturing the value of the state S, right? So if the state S is good, that means that this state is a good initial state. If you start with this state, you can accumulate more rewards. And also this describes, the kind of the goodness or the quality of the policy. If the policy is good, then this value would be high, right? If the policy is just keep doing the right thing, you get more and more reward. So, so in some sense, you can say that, you can say that actually your problem is really just trying to figure out what's the right pi that can optimize your value function. So you can reformulate the problem. Before we are trying to find the sequence of action to maximize the reward, right? So now I think we can just change our perspective, saying that we are trying to find out the policy such that I can optimize my value function. So basically, your new goal is that you are maximizing over all policies. You maximize this v pi as 0. So here I'm assuming as 0 is deterministic, is given. So okay, maybe I should just So suppose you are given some S0, right? So that the question is that S0 is given, and you are just basically maximizing. You are trying to find out the best policy such that the value of S0 is maximized under this policy. Okay, so right. So basically, in some sense, if you can see, if you can find out what this function is, v pi S0 for every pi, if you can know. For every policy, suppose you can figure out this number, then you can just enumerate over all policies and see which one has the best return, total return, right? So of course that might not be our efficient algorithm, but conceptually that's what we're trying to do, right? So you're trying to figure out what's the reward for every policy, and then you try to pick the best policy. So basically computing this v pi, computing this is this is called sometimes called policy evaluation. You are evaluating how good this policy is. And once you know how to do the policy evaluation, then you can try to do the policy maximization, right? To maximize over the policy. So the first thing I'm going to answer is how do you do the policy evaluation? So how do you do it? It turns out that basically you just have to do a recursion. So to do policy evaluation, you just do some recursion. So what does that mean? So I guess suppose you think about the policy as state S, right? So let's just use the definition. The definition is that basically you start from state S, and then, right, the definition is that you say this is the expectation of this, the total payoff, discounted payoff. Assuming that you start with state S0 is equal to S. And because S0 is equal to S, right, so you just say this is equals to RS. This is the reward that you get in the first step. And then you say you have some discount factor. You pull one gamma off because all the other terms has one gamma there. And then you say this is RS1 plus gamma RS2 plus gamma square RS3, so on and so forth. Note that I pull one gamma out, right? So before it was gamma square RS2, but now it becomes only one gamma. Right? And if you look at the rest of this term, this is something that is actually something we have kind of like, this is also meaningful in the sense that this term is really just the total payoff obtained from starting at S1, right? Basically, this is just that you start with S1 and you apply this policy iteratively, and what's the payoff you should get, right? Without the gamma. The gamma is a factor, right? So without the gamma, right, this is basically the total payoff if you start with S1. Right? So that means that this quantity is really literally just V pi S1. So that means that you got a recursion in some sense between v and v pi, between vs and vs1. So maybe just more formally, so I can write this as this. So I think maybe technically I should say that without expectation, this part is equals to. Okay, I guess, let me not be too technical here, but you can probably see what I mean. So here, v pi s1 is basically the reward you get from executing from s1. But why I'm still having expectation here, this is because s1 is also random. Right? It's not like S1 is deterministically determined. S1 is drawn from this environment, right? Like, so S1 has this distribution. So S1 is drawn from P S0, A0. And A0 is pi of S0. So this is P of S0, pi of S0. Any questions so far? So maybe just to be more explicit, basically this is equals to R of S plus, if you write out this expectation, you can write it as a sum. So basically you draw S1 from this distribution. That means that it means that you just say for every possible S1 in a set S, you look at the density of S1. This is the chance that you see S1 in the next step, and then you times v pi s1. That's just how I expanded it, the definition of expectation. I think maybe people typically, when sometimes, it doesn't really matter what variables I use for s1, right? I can use any variable, so maybe let's just use s prime, just to be consistent with a typical notation. So basically you loop over all possible s prime, all possible next state, and you first say, I'm looking at what's the chance to arrive at that state s prime. And then I multiply that with the value function at s prime. So this is just equivalent to this expectation above. Okay, so why this is useful? So first of all, let me say this is called Bellman equation. This is an equation about the value function v pi, and it's often called Bellman equation. So and also this is technically I think if you don't really want to have sometimes this is called Bellman equation for v pi because there's going to be another Bellman equation which has exactly the same name. People also call it Bellman equation for some other quantities I'm going to define in a moment. So this Bellman equation, why is useful? It's useful because this is a linear function in v pi s, right? So you can think of it as, maybe I'll use here. So you can think of v pi 1 up to v pi m. Recall that m is the number of states I defined. So you can think of all of this as the variables, as m variables. And the Bellman equation gives m equations about these variables. Right, why there are m equations? Because for every s, this is true for every s, right? For every s, it has an equation that involves these variables, v pi of s and v pi of s prime, in a linear way. So Bellman equation is a linear system of equations in this variable v pi 1 up to v pi m. So so to figure out what is v pi I, you just have to solve the system equations. I'm not sure whether is this too abstract? So in some sense, maybe just give you a concrete example, right? So for this concrete example here, if you write out this Bellman equation, what will happen is the following, right? So you probably for the concrete example, you have maybe something like v pi. I'm just plugging in some concrete thing, like maybe 6. So you are trying to figure out what's the equation for v pi 6. V pi 6, if you think about the equation, your first thing is the R6. This is the reward you get in the first step, and then you times gamma times the reward you get in the future, right? So where you have the sum, right? Sum S prime in S, PSA, something like S prime, V pi S prime, right? And you plug in all of these numbers here, and then you get an equation which depends on V pi 6 and all of the other V pi S prime. But this is a linear equation, right? So think of this as a variable, all of these as variables. This is an equation with a bunch of variables, but they are linear in those variables. And you can write this for everything, right? You can say this is R5 plus, and you have the system equations, right? Each equation is a linear equation in the variables. So basically this means that it's just computing V pi S for every S by some linear equation solver, by solving the linear equations. And because they are linear, you can use the efficient solver, like how do you solve linear equations? You can, I guess one way to do it is do some inverse of the matrix. Maybe there are other ways to do a linear equation, but that's a submodule that you can just invoke. You can invoke some off-the-shelf algorithm to solve the linear equation. Any questions?
Infinite solutions.
Can you say again?
Probably there are infinite solutions for linear.
Is it possible that there are infinite number of solutions? So I think in this case it's just not possible. Why it's not possible is probably not super obvious to see. In some sense, like you have at least it passes the trivial sanity check, right? If you count how many equations, how many variables, they are exactly the same. So typically you probably should have a unique solution. And I think in this case you can prove that there is a unique solution. Because this set of equations has some special properties. But maybe let me not get into that too much. Yeah. Okay, great. So we know how to. So basically, we know how to evaluate V pi S.
In this equation, PSA would be different depending on the initial state, right?
Can you say it again?
PSA
This one?
and probability. Yeah, would be different depending on the initial state.
No. This PSA S prime. This P is the dynamics, right? It's the transition probability, which is global, which is kind of like what you. It's a given property of the MDP.
For example, if you subtract the first equation to the second one, would be just R over 6 minus rho over 5.
If you subtract these two?
Yeah.
Oh no, because right. So that's a good point. Sorry, I think this S and A, I think I only partially replaced this. This will be 6. Yeah. Oh, is that what you're asking? Okay, cool. Sure. So I think this will be. Yeah. That's a great question. So this should be 6 and also pi of 6. So and then if you write this, then you have gamma 5 pi of 5 s prime, v pi s prime. So all the coefficients are different for different equations, different lines. Yeah, thanks. Okay, cool. So we have computed the v pi. But the next question is how do you, so basically we have solved the policy evaluation. Now we need to figure out how do we maximize the policy, how do we find out the best policy. So let me find out some places. It turns out that you can use a similar technique to find out the best policy. So here is some definition. So first of all, let's define V star S to be max pi V pi S. So what does this mean? This means that you are looking at all the possible policies that you can use starting from S. You look at you basically try all different policies starting from S, and you ask which policy gives me the best reward, total payoff, and the value of that total payoff will be the V star S. So V star S is the intrinsic value of the state S, right? So you're saying that the state S, just how valuable the state S is, right? And how valuable is measured by using the best possible policy, right? V pi S depends on both the pi and S, right? Like if you use a bad policy, V pi S may be low, but V star S is saying that what's the value of this state if you use the best possible policy in the future steps. And then you can also define the so-called pi star. This is the so-called optimal policy. This is equals to the argmax over pi V pi S. Right? This is asking, what is basically you are just doing exactly the argmax of the previous thing, right? So the best policy that achieves the max measure is defined to be the pi star. This is the optimal policy we are trying to find out. Okay, so with these two notations, I think I can. So I'm going to first find out the V star S, and then the pi star S, will be relatively easy to do because as you will see. So the first question I want to answer is how do we find out what's the V star of S? What's the intrinsic value of each of the states? So it turns out that you can do a similar type of Bellman equation as the V pi, but just the whole thing involves a lot of max operators. So here's what I mean. So if you think about the V star S, again you try to get a recursion for V stars because V stars is kind of complicated because it depends on all the future states. So you want to have a recursion. So I'm going to be a little bit the exact mask here. I think if you want to make it rigorous, you have to justify more formally. But I'm not going to deal with that. So I'm going to be slightly sloppy here, just for simplicity. So you take an argmax over pi Rs plus gamma So this here I'm using the Bellman equation I just derived, right? So this is the Bellman equation I just derived. So because V pi S is equal to this, right? And so let's think about this, right? So first of all, you're maximizing over pi, so this one doesn't depend on pi even, right? So you can just take it out. So you just say this is R of S plus okay, so now you look at this thing. So pi shows, you want to maximize this, and pi shows up in several different places, right? Pi shows up here, and pi shows up here, right? So the pi shows up here in the sense that if you use different pi, you're going to have a different transition probability so that you can arrive at different set of state S prime with different probabilities, right? And this pi here is trying to capture what happens after this step, right? So after you already see S prime, what's the future reward, right? This V prime S is basically telling you, if you arrive at S prime, what's the future possible payoff after S prime. So I'm going to so I'm going to be a little sloppy here, but let's say suppose we optimize this first V pi S, first, right? This occurrence of pi's, right? So if you want to choose the pi such that this is the best, what you should do. So what you should do is you should try to figure out, you should try to make the pi of S give you the best action, right? So basically what I'm saying is that this is equals to, maybe let me write it down and then it's easier to explain what I want to prove. So basically I'm saying that I'm going to choose the pi of S to be the action A that maximizes this, right? So pi of S is some action, right? So I just write A here, and I say I try to choose the best A such that pi of S is equal to A, and I still want to maximize this. However, pi affects two things, right? Pi also affects what happens in the next, right? So then I need to also try to make sure the pi makes the future steps the biggest. So, and then the nice thing about this is that this term is something I already defined, which it's a recursion, right? This is just V star S prime. So basically, if you look at the final equation, it's kind of like you are trying to try all possible action A's you take at this step, right? That's why you take max, right? So you try all possible A's and use, I guess, sorry, my bad. For any possible A's, you have a probability to arrive at S prime, right? And then you say that after arrive at S prime, after that you use the optimal policy V star S prime, starting from that. And this is basically this part is the reward, the best reward you can get if you apply action A at this step, right? If you apply action A at this step, what's the reward you can get? You're going to have some transition probabilities to arrive at S prime, and then after you arrive at S prime, you have some maximum possible reward V star S prime. So that's why the sum is the best possible reward you can get if you apply action A at this step, and then you max over A, and that's the best thing you can do.
So I guess it's similar to earlier when we were finding out the entire policy. Now to find the optimum policy, again we have equations with n variables, and we solve for all of those to get the optimum policy.
Yep. Okay. So that's the next step. That's a good question. So. But maybe just any other questions before we move on to the next step? Okay, so you get great. So you get the equation, and okay, let's see what equations, right? So you have, for every S you have an equation, and so you have the same number of variables and the same number of equations, right? The M variables and M equations. But the problem is that now the equations are not linear anymore. Right. So they are not linear equations. So you still have a nonlinear equations that involves m variables, and you have m of these equations. So that's the challenge, right? So there's no any off-the-shelf solver you can use to solve these sets of equations that are nonlinear. So that's why we need to introduce this so-called value iteration. Let's see. So how do we solve these equations? So we solve the equations by the so-called value iteration. So first of all, let's just think of this V star let's just define a notation v star to be v star 1 up to v star m. This is a vector in Rm. Okay, so I view this function as a vector because I only have n possible inputs. I can view this function as a vector of dimension n. Okay, so and I'm going to say that and then my equations can be written as this, right? So it's kind of like v star equals to 1 is equals to something like, maybe let's just say each of these equations is like this, right? R1 plus some max, something like this, right? And v star is 2 is equals to R2 plus max, something like this, right? That's my system equations that I have so many equations. Each equation is look like this. And I can abstractly write this as the following. So I can abstractly write this as this whole vector. Let's call it v star. And the right-hand side is something that involves v star again, right? So you call this whole thing b of v star. So basically, this is just a function of v star, right? So I'm just abstractly writing as a function of v star, which gives you a vector. This is also a vector. So then if I do this, then basically my equation can be written as v star is equals to b of v star. I'm not doing anything deep, it's just rewriting the thing with a very abstract notation, right? So this is the form of my equation. V star is equal to b of v star. And b of v star is just the right-hand side of the Bellman equation. Okay, so, so what I'm going to do is that the algorithm is very simple to find out the equation. So this is kind of taking inspiration from the so-called fixed point problem in math. If you haven't heard of it, don't matter. Doesn't matter. It doesn't matter. Don't worry. It doesn't matter. But roughly speaking, the thing is that you think of this b as some kind of operation, right? So you say that this v star is a fixed point of this operation. You apply this operation on a v star, you get arrive at the same thing. So that's the connection to the so-called fixed point problem. But if you don't know the connection, basically somehow there is some theory in math which says that if you want to solve this kind of fixed point problem, you just have to iterate until it converges. So what does that mean? That really just means that you have this so-called value iteration. So what you do is you say you initialize some v in this dimension r to the m. Maybe you can just do v0. I think that's fine. You just initialize, somewhere randomly, or maybe just initialize to 0, and then you just have a for loop. So you have a loop such that at every time you say v is updated to be b of v, and you just keep iterate. And there's a guarantee that you will converge to the fixed point. The fixed point will satisfy v is equal to b of v, and that's the v star. And this update really just means what? This update just really means that you say vs is equals to rs plus basically the max right-hand side of the Bellman equation. So this is what it really means, right? When you really implement an algorithm, you say you compute the right-hand side of the Bellman equation with the hypothetical v, right? And then you give this value to the new value of v, right? You update the new value of v by the right-hand side of the Bellman equation. Here I'm using this, right? Means that I compute this value and then I give this value to the vs. Do I guarantee that? Yes. So I think you can guarantee that there is a unique one and you can converge to it in a certain amount of time. I think that's the homework question. Yeah. So to do that, you have to. I think the homework question has some hints on it, right? So you basically compare the distance between this v and a true v, and you can see that the distance between this v this working V with the true V star is kind of shrinking iteratively. Okay, I think I'm running quite, yeah. So there's one other algorithm which is called policy iteration, which is very similar. But I think I'll just leave that to you for reading the lecture notes. Like it's basically kind of like it's also kind of not required for homework, so just optionally you can read it if you're interested. Okay, thanks.